Hey everybody. Today we're using R to do calculations involving the binomial distribution. There are four basic functions in R that you're going to want to know. First of all, rbinom is going to generate random values in the binomial distribution with a given size and probability of success on an individual trial. For instance, rbinom of 10, 2, 0.5 generates 10 random values from the binomial distribution with sample size 2 and probability of success on any individual trial of 0.5. Secondly, dbinom is going to return the probability of getting a specified number of successes in that same binomial distribution with a specified sample size and probability of success. One nice thing here is that you can specify x as a vector. In other words, you can compute probabilities for different numbers of successes all at once. For instance, dbinom 0:4, 4, 0.5 computes the probability of success, probability of getting 0, 1, 2, 3, or 4 successes in a binomial distribution of size 4 with probability of success of 0.5 on any individual trial. Next is pbinom. This is a cumulative probability function. It's returning the probability of getting at most x successes in that same binomial distribution. Again, you can feed a vector value in for x. So, for example, pbinom 0:4, 4, 0.5 returns the probability of getting at most 0 successes, at most 1 success, at most 2, 3, and 4 successes in that same binomial distribution of size 4 and probability of success 0.5. Finally, qbinom is a sort of inverse probability calculator. It's going to return the smallest value x such that pbinom of x in that same binomial distribution is q. Another way of saying this is that qbinom is computing quantiles in that same binomial distribution. For instance, qbinom of 0.25, 0.5, 0.75, 10, 0.5 is going to give you the 25th, 50th, and 75th percentile in the binomial distribution of size 10 with probability of success 0.5. We can kind of verify this by using the pbinom function. So let's get the cumulative probability of 3, 4, 5, 6, and 7 successes in that same binomial distribution. You can see the probabilities there. So, based on this, we can see that x equals 4 is the first value where the probability is over 25%. X equals 5 is the first value where that probability is over 50%. And x equals 6 is the first value where that probability is over 75%. Let's do some actual problems. First of all, let x represent the number of 6s in 10 rolls of a fair die. Simulate 50 runs of this probability experiment. Here we're going to want to be generating random numbers. We're going to be using an rbinom command. So let's swap over to R and do it. Rbinom. We're going to need 3 arguments. First of all, the number of times we're going to want to generate random numbers. Second of all, we're going to specify the size for the binomial distribution we're going to be using, and then the probability of success. In this case, 1/6. So we get 50 random numbers, all between 0 and 10. We can summarize what we've got here using the table command. Let's do that really quick. Overall, we've gotten 12 zeros, 20 ones, 13 twos, 3 threes, 1 4, 1 5, and no values greater than 5. Problem 2. According to a recent survey, 72% of Americans prefer dogs to cats. If 8 Americans are chosen at random, what's the probability that exactly 6 prefer dogs? That fewer than 6 do? In this case, we're computing probabilities in the binomial distribution. In the first case, it's a probability that we get a specific number of successes. In the second, it's a cumulative probability. So the first part here, we're going to use a dbinom, and in the second, a pbinom. All right, so to get the probability of getting exactly 6 successes in 8 trials, We're going to use dbinom. We're going to, first of all, say the x value that we're interested in, 6, then the sample size, and the probability of success, 0.72. So there's a 30.58% chance that 6 of the 8 people surveyed will prefer dogs to cats. Now we'd like to know the probability that fewer than 6 do. This is going to be a pbinom, a cumulative probability question. You have to be a little careful here. The number that we're actually interested in is 5. We want the probability of getting 5 or less, which, to say slightly differently, is fewer than 6. And of course, the binomial distribution we're looking at is going to be exactly the same. 8 trials, a probability of success on each trial of 0.72. So the probability of getting fewer than 6 people that prefer dogs to cats is about 39.73%. Problem 3. A weighted coin has a 42% chance of coming up heads. What's the expected number of heads in 5 tosses? The standard deviation? Construct a probability histogram for this random variable representing the number of heads in 5 tosses. So we're in the binomial distribution with size n and probability 0.42 of success. So let's generate the discrete probability distribution here, compute the mean and standard deviation, and then get that histogram. So first of all, let's encode the possible values that we could get here from 0 to 5. So x is 0, 1, 2, 3, 4, and 5. Now let's get a vector of probabilities. Each one is going to be a dbinom. We are going to want to do all of the values of x from a binomial distribution of size 5 and a probability of success of 0.42. And so P is a vector of probabilities. Of course, its sum should be 1. Fantastic. We can get the expected value of this by using a weighted mean. We want to get the mean of all those x values weighted according to their probabilities P. In this case, 2.1. We can do the variance by doing a weighted mean of the difference between the x values and that mean squared, again weighted according to the probability. The variance is 1.218, and to get the standard deviation, we need the square root of the variance, so 1.10363. Let's wrap up by getting this probability histogram. We're going to use the tidyverse. We'll use the ggplot2, so let's first load that in. The ggplot2 package is by far the best way to do graphics in R in my experience. I strongly recommend not using base graphics. The quickest way to get a decent probability histogram is using the qplot command. We're going to want to plot the x values here on the horizontal axis. We're going to want to weight them according to their probabilities. We're going to want to get a probability histogram, so the geom is histogram. This is how we tell R how we want to display the data. Great. Now, this command isn't going to give us a beautiful histogram yet, but let's take a look at it just for reference. We'd like these bars to be touching. We'd like to be able to tell the bars apart. So in order to fix all of that space in between the bars, I'm going to tell R to use exactly 6 bins. And let's just do a little bit of boundary. Let's get a boundary color of black. That way we can tell the bars apart. So there's a probability histogram for this particular binomial distribution.